SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 15, and today we are going to discuss what is called stress strain relations. So, let me begin with the motivation for this topic. So, suppose that we have this reference configuration of a body which is getting deformed, right, and the reason that the body is getting deformed is because it may be subjected to external load on some part of the boundary of this body, and in some other part it might be clamped, right. So, what is our goal? Our goal is to find out the deformation in the body. So, we have the body, it is subjected to load, and we want to know what is the final deformed shape of the body. We also want to know what is the stress that gets generated in the body, so that we can be sure that okay, the stress is within the prescribed limit, so that the body is not failing or does not fracture, right. So, basically the goal is to get the deformed configuration and what is the stress generated in the body, right. So, how to solve that? So, we have already derived the equations of equilibrium. So, if we can recollect it, the equations are del sigma 1 over del x 1 plus del tau 1 2 over del x 2 plus del tau 1 3 over del x 3 plus the body force in one direction, and that should be equal to density times the acceleration in one direction. So, this is one of the equations. Likewise, we have two other equations which are del tau 2 1 over del x 1 plus del sigma 2 2 over del x 2 plus del tau 2 3 over del x 3 plus the body force in two direction, that is equal to density times the acceleration in second direction, and the last equation is del tau 3 1 over del x 1 plus del tau 3 2 over del x 2 plus del sigma 3 3 over del x 3 plus body force in three direction is equal to rho times acceleration in the third direction, right. So, let us have a look at these three equations and see how many unknowns are present here. So, you see we have the components of the stress matrix sigma 1 1 tau 1 2 tau 1 3 tau 2 1 sigma 2 2 tau 2 3 and likewise. So, there are 9 components of stress matrix, and we know that stress is symmetric. So, we have basically 6 components of stress matrix unknown here, right. So, 6 stress components are unknown. Then the body force B 1, B 2, B 3, they are something which are prescribed. For example, if you have gravitational body force, the body force becomes rho times acceleration due to gravity. Okay. So, these are basically known. Usually known. And then on the right hand side we have acceleration. So, acceleration you can write in terms of displacement, is not it? So, if I come back to our picture here, so you can recall when we were working on strains, we had a material point x which was getting deformed to some point small x, right, and then we have this coordinate system. So, this position vector in the reference configuration. So, this is the reference configuration relative to which we measure displacement, right, or relative to which we also measure the strain. So, this is the reference configuration, whereas this is the deformed configuration. So, in the reference configuration, any particle is denoted by its position vector big X, and in the deformed configuration it goes to small x, right. And the line connecting small x and big X, that is the displacement, is not it, that is u, which is different for different particles. So, u is therefore a function of x, the particle, and also the time t. So, for a given particle the displacement is u of x, and as time progresses u is also changing. So, what would be the velocity for a particle? So, the velocity for a particle, so v for a particle big X comma t is then simply the del u by del t, keeping the particle fixed. Do you see this? See, while taking the derivative we do not have to change the particle, because we are measuring the velocity of a particle. So, therefore, the big X should not change, because big X denotes the material particle. As you change big X, you are talking about different particle. So, for a particle big X remains fixed, and when we talk of the velocity of a particle, it is simply del u by del t at constant big X. Okay. And we could also write this as u with a single dot of big X comma t. Likewise, what is the acceleration? So, acceleration would then be u double dot of big X comma t, which one could also write as del of velocity by del t at constant x, keeping the material particle fixed. You know, there is one thing to note here, that the velocity and acceleration we are writing it in terms of the material particle's coordinate big X, the coordinate of the material particle in the reference configuration, which is big X, right. So, this is also called Lagrangian description. So, I will just write here, when we describe velocities and acceleration and any other thing in terms of position of the particle in reference configuration, which is big X, then we call it Lagrangian description. Okay, it is just a name. some of you would also be taking fluid mechanics courses, and in fluid mechanics they describe velocities and acceleration in terms of not the Lagrangian description, but what is called the Eulerian description, where the velocities and acceleration are written with respect to the current position of the particle, that is small x. Okay. But here what we are doing is called Lagrangian description. You will also notice that in fluid mechanics, when you do it in the Eulerian description, the formula for acceleration gets complicated. It has what is called local acceleration and also convected acceleration, but we will not go into that. When you learn fluid mechanics, you will of course go through those topics, but here when we say that acceleration is simply del v by del t at constant big X, that means we are keeping the particle fixed, then this is Lagrangian description, okay, and it is simpler here, whereas in fluid mechanics things get difficult. Anyway, with these knowledge of velocity and acceleration in terms of displacement, you could see that acceleration 1 is then simply u1 double dot, is not it? The rate of change of coordinate in the one direction u1, we have to look for its second derivative. Similarly, acceleration 2 would be u2 double dot, and acceleration 3 likewise would be u3 double dot. Okay. So, basically we have written acceleration in terms of displacement, right, its time derivative. So, what are the unknowns here? Can you see? It is the 6 stress components and the 3 displacement components plus 3 displacement components. So, we have actually 9 unknowns, is not it, but only 3 equations. See, we have already used the symmetry of the stress tensor, that is why we have only 6 stress components as unknown, otherwise we would be having 9 components as unknown. So, we have no other equation to use, we have only 3 equations, but 9 unknowns, we cannot solve it, right. So, we need something more, so that we can solve this equation, and that something more is what is stress strain relation. Okay. So, I will write here, we have 9 unknowns, but only 3 equations. Therefore, we need extra equations to solve the above problem, and that extra equation is given by what is called stress strain relation. Okay. So, that is the motivation for this topic. So, being able to write down stress in terms of strain. Do you remember that strain epsilon and stress is sigma, of course. So, epsilon is half of grad u plus grad u transpose, right, or in terms of components epsilon I j is half of del u I over del x j plus del u j over del x I. So, we can write strain in terms of displacement, and when we can write stress in terms of strain, then indirectly we are actually writing stress in terms of displacement, is not it? So, when we come back to our equation, the 6 stress components through stress strain relation we will be able to write in terms of displacement, and then we have only the displacement as unknown, is not it, the 3 components of displacement u1, u2, u3, and we also have 3 equations. So, we can now go ahead and solve these equations, right. Okay. So, I hope the motivation is clear for the stress strain relation. Many places it is also called constitutive relation, constitutive. Okay. So, the relationship between stress and strain is called constitutive relation, all right. So, let us see how can we relate stress and strain. So, relating sigma in terms of strain. Now, notice that stress has got 6 independent components, and likewise strain has also got 6 components. Strain is also symmetric. So, it has only 6 independent components. So, in general, each of the stress components will depend on all of the strain components. What I mean is that sigma 1 for example, will depend on epsilon 1 epsilon 2, epsilon 3, epsilon 1 epsilon 1 and epsilon 2 on each of the 6 components. Similarly, sigma 2 will depend on all the 6 components, sigma 3, sigma 1 sigma 1 and sigma 3. So, they depend on all the 6 components. So, you can see that it is not a simple function, it depends on 6 variables. And how it should depend? Will it depend linearly? For example, will the sigma be simply proportional to strain, or will there be quadratic dependence? Will sigma 1 be, let us say, some constant times epsilon 1 square, or sigma 1 would be equal to log of epsilon 1. So, what will that function be? So, that is of course, you can't get it mathematically, and mechanicians do experiment to obtain this stress strain relation. Okay. So, it is usually obtained through experiment. All right. But we can still do some mathematics. So, stress is some unknown function of strain, and that function could be logarithmic, trigonometric, polynomial, anything. But if you recall your first year mathematics, you can write any function and expand it in its Taylor series. So, you can write any function as a polynomial function, but the Taylor series of course never ends, it goes up to infinity. But the nice thing is you have written your function in terms of polynomials as a polynomial. Okay. So, you can do the same thing even for the stress components. So, for example, sigma I j, where I j could vary from 1 to 3, which is a function of strain epsilon k L. Okay. So, k L is also for all the 1 to 3. So, all 6 components are present here. So, this is an abstract notation for dependence of stress on strain. Now, let us do its Taylor's expansion about 0 strain. So, look at this picture above. When would the strain be 0? So, strain is obtained from the gradient of displacement. Of course, if the displacement is 0, then strain is also 0, right. Or if the displacement for each of the point in the body is the same, then gradient of u would be 0 and then the strain also becomes 0, right. So, if the body is going pure translation, every particle of the body undergoes same displacement. So, gradient of u would be 0 and so the strain is also 0, right, because it is half of grad u plus grad u transpose. And of course, if u is 0, then also strain is 0. So, when we say strain is 0, we are basically referring to the configuration of the body in the reference configuration, is not it? There is a case when u is same for every particle. So, in that case it simply undergoes rigid translation, and when it undergoes rigid translation, the shape of the body is preserved, right, it acts like a rigid body. So, the shape of the body would be same as it is in the reference configuration. So, we can say that when strain is 0, we are basically talking about the state of the body in the reference configuration. Okay? All right. So, we want to do the Taylor's expansion here with respect to the reference configuration of the body when the strain is 0. So, we would say that this is equal to sigma I j when each of the strain components are 0, right, plus the first derivative of stress with respect to strain, which is del sigma I j over del epsilon k L into epsilon k L minus 0, and then we have a summation here over k and L. There is not single epsilon here, right. We have epsilon 1 1, 2 2, 3 3, there are 6 of them. Okay. So, that is the first term, and then the second term in Taylor's expansion we also have the higher order term. So, it would be 1 over 2 factorial, then del 2 sigma I j over del epsilon k L times del epsilon m n into epsilon k L into epsilon m n plus dot dot dot. So, you can keep on going. See the first term here, if it is not 0, then it tells me what is the stress when the strain is equal to 0. So, in the reference configuration that we have chosen, if there is some stress in the reference configuration, that is this first term here. Okay. We could also write it as sigma I j naught, because it is at epsilon equal to 0, and this is also called residual stress. So, what is the stress remaining in the reference configuration, that is the residual stress, okay. And most of the time it is 0. Okay. So, I will just write here most of the time it is 0. And let us assume in this course that it is 0, okay, just to simplify our analysis. And also see the second term here is linear in strain, right. It has the derivative times the strain. So, it is linear in strain. The third term is quadratic in strain, because it has epsilon k L into epsilon m n. So, it is quadratic combination. The fourth term will be cubic, and likewise it will keep on going. But if the strain is small enough which is the domain of this course. Okay. If the strain is small, we can neglect the higher order term and just be happy with the linear term, is not it? Think for example, if epsilon 1 is 0.1 or it is 0.01, what will be epsilon 1 square? It is 0.01 whole square, that is much smaller than epsilon 1. What would be epsilon 1 cube? That is even smaller, right. So, you can neglect those higher order terms and just be happy with the linear term, right. So, that is what is done usually, assuming that strain that gets induced in the body is small enough. So, we can write that if the strain is small enough, okay, and sigma I j naught is also equal to 0, then we can write sigma I j as summation over k L of del sigma I j over del epsilon k L times epsilon k L. Okay. And you have two summations here actually. So, one is over k going from 1 to 3 and then L also going from 1 to 3. Okay. So, we have a linear relation. So, this is called linear stress strain relation. Okay. And what about this derivative here? You know, the derivatives are also evaluated in the reference configuration, that is the Taylor's expansion. No, each of the derivatives are to be evaluated with respect to the reference configuration. So, this has got a name, you know, this is called CIJKL. Okay. It is also called as stiffness tensor, fourth order, it is fourth order because you see it has got 4 index. If it is second order sigma for example, it has got only 2 index, but this has got 4 index. So, it is a fourth order tensor. Okay. So, this is defined as del sigma I j over del epsilon k L at epsilon k L equal to 0. When the strain is 0, you evaluate this derivative and then you call it CIJKL. All right. So, now we can also write that sigma I j is equal to summation over k L of CIJKL times epsilon k L. Okay. Now, can you see how many terms are there in CIJKL? How many components are there? You know, C1111, C1122, C1133, C1121, C1112. So, each of the index goes from 1 to 3, right. So, you have 3 into 3 into 3 into 3, 3 to the power 4. So, there are 3 to the power 4, which is 81 constants, that is a lot. So, even for linear stress strain relation, we need to have these 81 constants known for every material. You know, when you are doing simulation for an aluminum, you will require this stress strain relation, right, when you are solving for the deformation of an aluminum body, and then you need 81 constants for aluminum, is not it. Similarly, when you have wood, when you have any metallic body, any machines, when you are solving for the deformation of the machines, when you are solving for the stress generated in the machine, you require this relationship. So, you need 81 constants and they are called material constants, okay, because it varies from material to material. So, it varies from material to material. Okay. But it turns out, we do not really have 81 constants. You see, for example, stress is symmetric, right. So, sigma I j has to be same as sigma j I. Now, look at the right hand side. If sigma I j is same as sigma j I, does not that mean that C I j k L should be same as C j I k L? So, what I mean is, so since sigma I j is symmetric, this implies C I j k L should be equal to C j I k L. See, if it is not the case, then you work out this multiplication and sigma I j will never come out to be sigma j I. So, therefore, C I j k L must be equal to C j I k L for all I and j. So, this means C 1 2 2 2 should be equal to C 2 1 2 2, C 1 3 2 3 should be equal to C 3 1 2 3, and likewise for all of them. Only then the stress will come out to be symmetric, and we want the stress to be symmetric. No? So, we will work for a constitutive relation which gives me symmetric stress matrix. So, you can see that not all the 81 components here are independent. Likewise, because the strain is symmetric, that means epsilon k L is equal to epsilon L k, you can always force C I j k L to be equal to C I j L k. If C I j k L is not equal to C I j L k and you work out this multiplication, then you will see that the factor due to which k L and L k are not same does not really affect this summation, and that is because strain epsilon is symmetric. Okay. So, you can do some mathematics and show that C I j k L should also be equal to C I j L k. So, I will write here, since epsilon k L is symmetric, C I j k L equal to C I j L k, and when we choose it, it does not really bring in any constraint, because we finally have to work out this summation sigma I j equal to C I j k L into epsilon k L. So, we can always choose C I j k L to be equal to C I j L k, because the strain is symmetric. So, can you see how many constants are really now present in C I j k L, how many independent constants? So, from I j, because I j is equal to j I, so out of the 9 combinations of I j, we only have 6 of them which are independent, because I j is equal to j I. Similarly, from k L, only 6 of them are independent. So, finally, we have 6 into 6, 36 components. So, this means from 81, 6 square only 6 square, which is 36 components are independent. Okay. So, that is a good relief, is not it, from 81 constants coming down to 36. So, we need only 36 constants known for any material, and then you can get the stress strain relation. But it turns out, we can bring it further down. These properties, that C I j k l is equal to C j I k l or C I j k l is equal to C I j l k, these two, we say that this is minor symmetry, minor, it is a name. You can flip the first two index and you can also flip the last two index. So, it is a minor symmetry. There is another symmetry which is present in this C tensor, and it is that C I j k l is equal to C k l I j. So, you can flip the pairs, first pair and second pair, you can flip them, and this is called major symmetry. And why is it possible? Why does it happen that we can flip the two pairs? This actually comes from energy consideration. Now, let me try to prove it to you, how we can flip this. So, this basically comes from, so it comes from energy consideration, and I will explain to you what does this mean. So, let me give you an analogy of a spring. When we have a spring, what is the force that gets generated in the spring? The force is spring constant k times the elongation of the spring, right. Let us say that is x. So, force is equal to k times x. And what is the energy that is stored in the spring? Energy E, that is half k x square, is not it, which we can also write as half of k x into x, which is half of force times x, right. So, you see we have a single spring and the energy stored is half of force in the spring times the elongation in the spring. And in case of 3D body, what generates in the body is stress and strain, and we can make an analogy with the spring here. So, each of the strains epsilon I j could be thought of as the elongation in some spring, and each of the stress components could be thought of as the force that is getting generated in that particular spring. Okay. It is just that the force in the spring sigma I j does not depend only on the strain in that spring. So, sigma 1 does not depend only on epsilon 1, it also depends on epsilon 1 2, epsilon 1 3, epsilon 3 3, all the strain components. So, it is a more complicated spring, it is a coupled kind of spring that you can think of for a 3D elastic body. Okay. So, if you allow such an analogy, then the energy stored, the strain energy, we say when the body gets deformed, it stores some energy. You do some work on the body and the body gets deformed. So, where does that work go? It goes into storing energy in the body. It is stored in terms of what is called strain energy, because the body is getting strained. So, it stores the energy in form of strain energy. Okay. and we talk of strain energy density. So, that is energy stored per unit volume. If you want to get the total energy that is stored in the body, then you have to integrate that strain energy density over the entire volume of the body. Okay? And the energy stored has got an analogy with the spring. So, E we call it strain energy per unit volume. Okay. So, this is written as half of summation over I j into sigma I j times epsilon I j. So, it is like half of f into x, but there we have a single spring, here we have got how many springs are there? So, I and j goes from 1 to 3, 1 to 3. So, there are 9 of them. Okay. So, half of sigma I j into epsilon I j. So, that is the energy stored. And now, let us write down sigma I j as a linear function of strain that we worked out just now. So, that means this becomes half of summation over I j k l, and sigma I j becomes C I j k l times epsilon k l, is not it. So, this is your sigma I j multiplied by epsilon I j. Okay. If you allow me, we can write it in a compact notation, half of summation over I j k l C I j k l times epsilon k l into epsilon I j. Okay. So, that is the energy stored per unit volume in the body, and just as an analogy from a spring, the force is k x, right. You see the force is k x. We could also write this as del E by del x, is not it. Half k x square, when you do del by del x, you simply get k x. So, with that analogy, we can say that stress sigma I j is then del E over del epsilon I j, or let us say, let us use m n, sigma m n, because we are already using I j and k l. So, sigma m n then becomes del E over del epsilon m n. All right. So, let us try to work out the derivative now and see what we get. So, we will have half of C I j k l times del epsilon k l over del epsilon m n, you see this, into epsilon I j plus C I j k l times epsilon k l into del epsilon I j over del epsilon m n, right, because C I j k l is a constant. So, it does not change with strains. So, while taking the derivative, it acts like a constant, and we only take the derivative of the strains. Now, what will this be, the derivative? Del epsilon k l over del epsilon m n. So, suppose we assume that each of these strain components are independent, epsilon 1 1 2 2 3 3 1 2 2 3 3 1, then del epsilon 1 1 by del epsilon 1 1 would be equal to 1, del epsilon 1 1 by del epsilon 2 2, that would be equal to 0, right, because we are assuming that they are independent of each other. So, you can see that the derivative would be 1 only when both the index match with each other. So, k should be equal to m and L should be equal to n, is not it. So, we could write this as delta Km into Kronecker delta Ln. So, you see you get 2 Kronecker deltas multiplied, because each of the index has to match. Of course, we know that strain is symmetric. So, epsilon 1 2 is same as epsilon 2 1. So, it gives some extra complication while taking the derivative, but let us forget about that for this calculation here. Okay. Likewise, this one would be delta I m times delta J n. And what does Kronecker delta does? So, you look here, we have delta K m and we have a summation over k. So, in that summation, only when k is equal to m is when we get 1, otherwise it is 0. So, that means the summation over k will be gone and k will be replaced with m, right. Likewise, look at this delta L n, and we also have a summation over L, right. So, that means summation over L will be gone and L will be replaced with n. So, basically this would then become half of summation over I j C I j times m times n into epsilon I j, is not it? You see the summations over k and L are gone and k and L have been replaced with m and n respectively. Likewise, what you get from the second term here? So, you see you have delta I m. So, the summation over I will be gone and I will be replaced with m, and likewise summation over j will be gone and j will be replaced with n. Okay. So, we will have C m n k L times epsilon k L, and here we have summation over k L, is not it? And we know that this is sigma m n. Okay. So, what can we do further? You see in the first term we have summation over I j. Can we not write I as k and j as L, because it is just a summation variable. So, you can replace them with whatever you want, right. So, this means sigma m n becomes half of summation over k L C k L m n plus C m n k L multiplied by epsilon k L. You see the two terms have been combined now. When you replace I j with k L, you can easily combine the two terms, is not it. So, now you have in both the terms you have summation over k L. So, we can write this as half of summation over k L of C k L m n plus C m n k L times epsilon k L, is not it. And you see further, if I define another C, some C tilde of m n k L times epsilon k L, where C tilde of m n k L is equal to half of C k L m n plus C m n k L. So, I am defining another C, C tilde, which is half of CKLMN plus CMNKL. Can you see that this is same as C tilde KLMN? C tilde MNKL as given here this formula, and when you work out C tilde KLMN, you will get the same formula. So, instead of Mn you write KL, and instead of KL you write Mn, and you will see that the two summations here, this first summation will go in the second place and second one will go in the first place. So, this is actually also equal to half of C M N K L plus C K L M N by definition, but you know that A plus B is equal to B plus A, right. So, therefore, C tilde M N K L is same as C tilde K L M N. So, you see that this C tilde has got a property that you can flip the two pairs M n and K L, you can flip. So, although we have a C, we can always find an equivalent C, which in this case is C tilde, so that it has this extra property that M n and K L can be flipped, is not it, and that is called major symmetry. Okay. So, here these two being equal, this is called major symmetry. Okay. So, now due to this major symmetry, there will be additional going down of independent constants. You know, from 81 we came to 36, 6 into 6, and due to this extra symmetry, can you think of how many independent constants we will have now? So, think of a 6 by 6 matrix. So, you have 6 from I j and 6 from K L, C I j K L. So, from I j you have 6 numbers, from K L you have 6 numbers, you form a matrix, and since you can flip them, that means the matrix will be symmetric. So, that matrix has got 36 components because 6 by 6, but since it is symmetric, so only 21 of them are actually independent. Okay. So, basically from 81, which was 3 to the power 4, we came down to 36 due to minor symmetry, and then from 36 we come down to 21 due to major symmetry. Okay. So, that is the number of independent constants that any linear elastic material will have. Okay. So, any general material will have maximum 21 independent constants. So, you can remember this, I will also write it here. Any general linear material, you know why linear? Because we are talking of linear stress strain relation. So, linear material will have maximum 21 independent constants. Okay. Finally, there is one additional thing here. Now, there is something called void notation, VOIGT, void notation. You know, because stress is symmetric. So, if I write down the stress matrix, sigma 1 1, sigma 1 2, sigma 1 3, and this is also sigma 1 2, sigma 1 3 because it is symmetric, then sigma 2 2, sigma 3 3, sigma 2 3, sigma 2 3. So, it has got only 6 independent constants, is not it? So, we can also think of a 6 by 1 vector formed by the 6 constants, 6 independent constants in this matrix, and the sequence in which we take those 6 components is taken in this way. So, we go along the diagonal, then along the third column and along the first row. So, you go in this sequence, and as you get the components, write them in the vector for sigma. So, this is sigma 1 1, sigma 2 2, sigma 3 3, then we have sigma 2 3, sigma 1 3, and finally, sigma 1 2. You can do the same thing for the strain matrix. So, you get a strain vector. Okay. So, we can call this as stress vector, and likewise you also get a strain vector. And you go in the same sequence to form your strain vector. So, you have epsilon 1 1, epsilon 2 2, epsilon 3 3, epsilon 2 3, epsilon 1 3, and epsilon 1 2. Okay. And because of linear stress strain relation, there will be a matrix which will relate these two vectors, and that is here. Okay. This is that 6 by 6 matrix, which is actually formed by the components of C I J K L. So, formed by C I J K L. We call this stiffness matrix. Okay. So, this is called stiffness matrix, 6 by 6 matrix. So, likewise you can also write epsilon in terms of sigma. So, epsilon vector is equal to some matrix times the sigma vector, and then you have the 6 by 6 matrix, and this is called compliance matrix. Okay. So, you have compliance matrix and then you have stiffness matrix, and you can see that they will be inverse of each other. Okay. And this matrix will be symmetric and it will have 21 constants. So, it is symmetric and therefore, it has 21 independent constants. All right. So, this was about linear stress strain relationship, and we see that we require 21 constants for every material. When you are working with aluminum, you are working with magnesium, you are working with stainless steel. So, whenever you have body formed by such materials, then for each of the materials you require these 21 constants in general. So, you need maximum 21 constants. And in the next class, I will show you there is a very simple isotropic material which has only 2 independent constants actually. So, from 21 you go down to 2 because those materials have got extra symmetry in addition to minor and major symmetry which every material has, because it is coming from mathematics, right. There are class of isotropic materials which have extra symmetry. So, we will learn about isotropic materials and other class of materials in the next class. Okay. Thank you.